In the previous lecture, we discussed about the work done in different thermodynamic processes, and also we seen that every process, that is a change of state of a thermodynamic system from one state to another, can be represented in an indicator diagram. Usually we will use the PV diagram, which consisting of the pressure along the y-axis and volume along the x-axis, and when a system changes from the state A to B, it can be represented by a curve. And also we have seen that the work done in this process is represented by the area under the curve. But you know that the area under the curve actually depends upon the shape of the curve. For the same endpoints A and B, we can have different curves. That is, the system may move through this path, or the system may move through this path, or the system may move like this. So here all in this all curves, the initial and final points are the same. That means the initial and final states of the system are the same. But since they are traversing through different curves, the area under the curve is different. Hence the work done in each process or each area under the curve will be different. That means the work done by a system depends not only on its initial and final states, but also on the intermediate states it passes through. That is, work done on a system or done by a system not only depends on initial and final points or initial and final states, but depends on the path followed in achieving the final state from the initial state. Now consider an ideal gas in two situations, but initially constrained to P1, V1, T1. That is, the pressure is P1, the volume is V1, and temperature is T1. In one situation, an isothermal work suppose it is allowing it to take up heat is done by the gas to attain a final state of P2, V2 and T1. This is the first situation. So that can be represented on the indicator diagram like this. This is the initial state P1, V1, T1, and this is P2, V2, T1 again. The state is A and state is B. It is, suppose this is the work done in changing from the first state to the second state in the situation 1. So this is the situation 1 by an isothermal work. Now in the second situation, the gaseous system from its initial state P1, V1 and T1 changes to the final state P2, V2, T2 through an adiabatic process. That is, we are supplying some quantity, small quantity of heat, so that its temperature also changed. On the indicator diagram, the states for the situation 2 will also be the same. That is, this is the P1, P1, T1, and this will also be P2, V2, T2. But the work done will be like this, some other curve. So on the indicator diagram, we can say that indicator PV diagram, both the states are same but have been obtained by giving different quantity of heat. So in situation 1, we are providing a quantity of heat Q1, and in situation 2 we are giving a quantity of heat Q2. So the quantity of heat absorbed by the system in two situations are different, but the final and initial states of the system during these two processes are the same. But even though the quantity of heat are different, the states of the system in the PV indicator diagram are same. So we can say that the quantity of heat, like the work done, are actual functions of the state of the system and do not depend upon the values of the coordinates of the system. That means these two functions depends upon the intermediate states in which it passes through, or otherwise we can say that the path of the process. So we can say that the work and heat are path functions. So the path functions are the functions or the properties of a system that depends upon the path through which the state is attained, and not depends only on the initial and final states of the system. Examples for path functions are work and heat. So path functions are the thermodynamic properties of a system or the functions that depends on the path through which the state is obtained. Examples for path functions are work, the heat absorbed or liberated by the system. Also, in some other cases, some of the thermodynamic properties of a system depends only on the initial and final state of the system, not depends upon the path through which the state is attained. These are unique functions of the system and have nothing to do with the path adopted for arriving at one state to another. Such functions are called point functions or state functions. So they are the properties of a thermodynamic system which do not depend on . depends upon the path through which the state is attained, but depends only on the initial and final state of the system. The examples for this point or state functions are, we will discuss it later. Now in the next lecture, the internal energy, so you may be familiar about the entropy. This internal energy, entropy, etc. are the examples for point functions or the state functions. Now we have to discuss this internal energy. So what we are discussed so far is that the thermodynamic functions or properties of a system can be classified into two: the point functions and path functions. The path functions are the properties or the functions of a system that depends upon the path through which the state is attained, and not only depends on the initial and final state of the system, but it depends on the path through which the state is attained. Examples for path functions are work and heat. And state functions are the properties of a thermodynamic system which depends only on the initial and final states of the system and not on the path through which the state is attained. So examples for state functions are internal energy and entropy. So one of the important type of energy which we will usually come across in thermodynamics is the internal energy. There are some thermodynamic systems which do not possess any mechanical energy, yet they are capable of performing work. Such systems are said to have an internal energy, which is also of two types. So internal energy is the energy possessed by a body or a thermodynamic system which is capable of performing work, which is not the actual mechanical energy. The system will not have any mechanical energy, but it will have a capacity to do the external work or to perform the work. Such energy is called internal energy. Like mechanical energy, we can have two parts, the kinetic and potential energy. Similarly, the internal energy will have internal kinetic energy and internal potential energy. This internal kinetic energy is due to the vibrations or translations of the molecules in a system. So vibrational or translational motion of the constituent molecules of a gaseous system gives the or contributes the internal kinetic energy. According to the kinetic theory, the molecules are always in a state of rapid motion in straight lines in random directions with all possible velocities. This part of energy is actually proportional to, that is, the internal kinetic energy of a system is proportional to the temperature. When heat is given to a system, it causes increase in its kinetic energy and thus the temperature. Now the second part of this energy is the internal potential energy, which is due to the attraction between the molecules. You know that there is an attraction between the individual gas molecules of a system, and this attraction between the molecules contributes to the internal potential energy. When heat is given to a system, a part of it is used in performing work against these attractive forces and results in a larger storage of energy. This energy is actually depends on the volume. So the internal potential energy is a volume dependent energy. So if you consider an ideal gas, we know that the intermolecular attraction or interaction in an ideal gas is zero. So the internal potential energy of an ideal gas is always zero. So an ideal gas possesses only internal kinetic energy. So this internal kinetic energy is actually, if you consider a gaseous system, the different atoms or molecules in a gaseous system are in random motions in random directions with all possible velocities. These random motions are the velocities of the molecules contributes the generates a kinetic energy which contributes to the internal kinetic energy of a system. Now you know that in a real gas there will be an intermolecular attraction between the constituent gas molecules, and this intermolecular attraction provides the internal potential energy. The previous discussion we mentioned that the internal energy is a state function or a point function. That means it depends only on the initial and final state of the system, not depends on the path through which the state has been attained. The internal energy is usually represented by the letter capital U. Now if UA and UB represents the internal energies of a system at when the system is in the state A and state B respectively, then the change in internal energy, this is the quantity which we can measure, the change in internal energy which is given by UA minus UB. It depends on the internal energy of the state A and internal energy of the state B, not depends on the intermediate steps or intermediate states of the system even it passes through. So that's all about the internal energy. Now we have to discuss about the first law of thermodynamics that we will discuss in the next lecture. Thank you.